Oops. There we go. Let's see here. Well, yep, I'll get started. Heavenly Father, we thank you for this day. Again, I thank you for this class. Just ask you to give us wisdom today, help us to understand a little bit more about differential equations and just your creation, Lord, that you have blessed us with. And just help us to glorify you and know what we do, Lord. In your name I pray, Lord Jesus. Amen. All right, so let me get into it. So today I want to tell you guys the rest of the story, in some sense, of the homogeneous problem. We've looked at the solutions by eigenvectors. We've looked at solutions by complex eigenvectors, right? But we've noticed that it's not always possible, right, to write down the general solution. You know, something's missing from the story that we've been telling so far. We don't have a complete solution set for the problem, you know. So the question again is how to solve dx dt. Oh, I guess I've been using, I forget what letter I've been using in here, but whatever, dr dt, let's say, equals to a times r, right? For a and n by n matrix, right? How do we solve this problem? And so I think what I want to do today to start with is just to show you an example which we can solve by direct methods, and yet it doesn't fit anything we've done so far. All right? So like, what would that problem be? Well, so this is part of the reason for this example is just to give you an insight as to how you would discover these things, even if you didn't know the story I'm going to tell you towards the middle of class. And so here's the problem. Suppose you're going to solve y prime 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 equals to 0, right? We can solve this problem. How do we do it? Integrate once, what do you get? Constant, right? Integrate again? Constant plus C2, right? Integrate a third time. We get 1/2 C1t squared plus C2t plus C3, right? So, all right. Now what does this have to do with eigenvectors and eigenvalues, and what insight does this give us? Well, let me show you. Remember, we can trade the given problem using reduction of order for a system of 3 differential equations, right? We can let x1 equals to y, x2 equals to y prime, x3 equals to y prime prime, right? And in view of this, we have x1 prime is x2, x2 prime is x3, and x3 prime is y prime prime prime, which is also known as 0, right? So apparently, if we convert this to a system of 3 differential equations, we have what? We've got x1, x2, x3 prime equals to what? What's my matrix? 0, 1, 0, 0, 0, 1, and then finally the last row is all zeros, right? And so here I've got x1, I've got x2, I've got x3, right? So this is the same problem rewritten as a system of 3 first-order differential equations, right? Using reduction of order. And so we can do our usual eigenvector thing on this, right? What happens? What's the determinant of like a minus lambda I for this thing here? Well, I got minus lambda 1, 0, 0 minus lambda 1, 0, 0 minus lambda. This is an easy determinant to calculate. Apparently we've got, you know, minus lambda cubed. So my eigenvalues are what? We have eigenvalue lambda equals to 0 with what? Yeah, with algebraic multiplicity, right? Of 3. What's the geometric multiplicity here, right? How many eigenvectors, how many linearly independent eigenvectors do we have? So let's work on that. So the question then is, I want a minus 0 times I times my eigenvector u equals to 0, right? So what's that look like? It looks like 0, 1, 0, 0, 0, 1, 0, 0, 0, acting on my u VW. Right, so what's that tell me? This system of equations is pretty easy to solve, right? I don't think we need row reduction for this one. So like here, first row gives me v equals to 0. The second one gives me w equals to 0. And the last one gives me nothing, right? So I have what? What can I say about u? U is what? U is free, right? So you could say u is equal to 1, sure. So we have eigenvector u, 1, 0, 0. That's my only eigenvector. Just one, right? So this means that the geometric multiplicity is equal to just 1. All right. So just to remind you guys, what's the difference between algebraic and geometric multiplicity? For an eigenvalue, the algebraic multiplicity is the number of the times that that eigenvalue appears as a solution to the characteristic equation, right? So algebraic multiplicity is a statement about the characteristic equation. Geometric multiplicity, on the other hand, is the dimension of the eigenspace corresponding to the eigenvalue. It's the number of linearly independent eigenvectors you get for that given eigenvalue. The theory says the following. There's a theorem that says that that 1 is less than or equal to the dimension of a minus lambda I, which is less than or equal to m sub lambda. So I'm saying this is the algebraic multiplicity. And this right here is the geometric multiplicity. So there's always at least one eigenvector for every eigenvalue. All right, always at least one. And there's never more than the algebraic multiplicity. Like if I have an eigenvalue 3, which is repeated twice, that means I cannot have more than 2 linearly independent eigenvectors with eigenvalue 3. That's the way the math works here, right? Now, it may or may not be the case that you actually have, the algebraic multiplicity equaling the geometric multiplicity. When that doesn't happen, we're missing something. See, because every time we have one of these that's not accounted for by an eigenvector, we can't use an eigensolution to cover that part of the solution, right? And that happened here for this example. Yeah? And it's a pretty simple example if you go back to where it came from, right? What happens if we write out... See, we have another way to solve this problem, right? Because we can just use the problem we found from... We can use the problem we have from... the solution we have from calculus right here and translate it, right? What's the solution? Directly from here. My solution, x, is what? It is y prime, y prime prime, right? And if I write out what that is specifically for the one I just found right here, you got yourself at what? 1/2 c1t squared plus c2t, that's my y, right? Plus c3, there's y. What's y prime? Y prime was c1t plus c2, and my y prime prime is c1, right? And so this is a really weird calculation I'm doing for you guys right now, right? I'm showing you an example of what I might call reverse mathematics. Reverse mathematics is maybe something like the idea is using a math that you already know to discover something about math you don't know. Yeah? Something like that. So we know calculus, and I'm using calculus to give us a window inside linear algebra we don't yet understand. Namely this algebraic versus geometric multiplicity deal. I can factor c1 out here, right? And I would have 1/2 t squared for my top component. I've got a t for my middle component. I got 1 down here, right? Plus C2. C2, I've got a t. I've got a 1. And I got a 0. And then finally, C3. And I've got 1, 0, 0. Right? Notice here that last part I just wrote, that's the eigensolution. How did the eigensolution look? You guys remember? What was the rule? Remember how the eigensolution works? Our eigensolution we write down R equals to e to the lambda t times the eigenvector, right? So here we've got e to the 0 times t times the eigenvector 1, 0, 0, right? But that is 1, 0, 0. So you see this right here, that's my token eigensolution. There's only one of them here, right? The question is, what on earth are these? What are those? How do we find those? Right? Because we can't always just start with a problem we can do calculus on, right? This thing I did with integrating y prime prime 3 times, that is not usually available to us, right? Not usually. All right, so I will come back and I will explain where those come from in terms of my next method in a little bit. But it's going to take us a minute to work out some things, all right? So I think I proved to you guys already that the matrix exponential is a solution matrix. I did that, right? Yes, no, maybe so? Okay. I defined the matrix exponential. What was it? Do you guys remember? Have I not done that in here? Not a word? This has not been talked about here at all.
Brand new.
Completely brand new? All right. Man, I just can't remember what I did in which class this semester. It's bad. It's bad, guys. It's bad. We're going over the same material in... this can't be. I must have done this in here. What's that?
I'm going to start writing it up there.
Yeah. All right. Well, this feels wrong to me that we haven't done this in here. Anyway, so here it is. E to the TA is the summation n equals 0 to infinity of TA to the n power over n factorial. And that is the identity plus TA plus 1/2 t squared a squared plus 1 over 3 factorial t cubed a cubed plus dot 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 dot, right? And I'm pretty sure we proved in here that ddt of e to the TA is equal to a e to the TA. And this means that, hence, e to the TA is a solution matrix. I'm pretty sure I did that in here. Because it would have been weird if I did this in Math 221, because I don't really talk about this stuff in there. This had to happen in here.
You did do this.
Yeah, I did do this here. All right. Good. So the matrix exponential is a solution matrix, which means that every column in the matrix exponential is a solution. All right? So, and I also mentioned to you guys that, in fact, the matrix exponential is a fundamental solution matrix because we can also prove, we'll talk more about this today, that e to the TA, the inverse to that, is actually just equal to e to the minus TA. So it's invertible. It's an invertible matrix, actually. So it's a fundamental solution matrix, which means that we could calculate the solution to this problem that we're looking at if we could calculate the matrix exponential. Can we do that here? I think actually for my first example, we can just do this directly. All right, check it out. So I have A, example 2. Yeah, thank you. Which is really example 1 continued, but we have A equals to 0, 1, 0, 0, 0, 1, 0, 0, 0. What's A squared equal to? No. We need to work it out. Something exciting is happening in the next room. I'm not sure what, but anyway. So when I multiply these matrices, I get 0 for my first column. Then I get 0 for my second column. It's starting to look like everything's 0. But check it out, the third one, this times that gives me a 1 in the upper spot right here. So it's only got one non-zero spot. All right? And then what's A cubed? A cubed is just, it's all zeros. All right? So this is a super nice example because we can actually just straight away calculate the matrix exponential directly. The matrix exponential is an infinite series of matrices, right? But most of those are 0. So see how it goes? E to the TA is what? So we have the identity matrix plus T times A plus 1/2 T squared A squared. And past that, everything is 0. All right? And so what we're looking at is 1, 0, 0, 0, 1, 0, 0, 0, 1 plus T times 0, 1, 0, 0, 0, 1, 0, 0, 0 plus 1/2 T squared 0, 0, 1, 0, 0, 0, 0, 0, 0. Which if we put this all together, we get one grand glorious matrix with a 1 in the first spot.
Isn't that supposed to be T or A
0, 0.
Isn't that supposed to be A squared instead of A cubed?
Oh yeah, yeah. Don't worry, I made 2 mistakes, so I fixed it. So I put A squared over here already, but yeah, that's supposed to be A squared. So that gives me 1, 0, 0 for the first column. For the second column, I get a T up here. Then I get a 1 from the first matrix. And then I get nothing from over here. My third column, I get, what do I get? I get 0, no. I get the 1/2 T squared from the last one. All right. And then, let's see here, I get a T from my middle matrix. And I get a 1. Do these look familiar? Yeah, but what are the, remember we proved that every column in the solution matrix is separately a solution to the differential equation, right? Look at what my solution is. It's a linear combination of the third column, the second column, and the first column, right? So this is my eigensolution. And these right here are something new. All right? So this is one possible way you can solve the system, is if you can calculate the matrix exponential, you simply take a linear combination of the columns of the matrix exponential. That's your general solution. All right? However, it's not always possible to just straight calculate the matrix exponential. Like generally speaking, the series does not truncate like it just happened in my example. So this example is very fortunate. Usually you can't calculate the matrix exponential like this as much as I wish you could. This does also exemplify an important theorem. Here's a theorem that we should know about. This is the so-called Cayley-Hamilton theorem. And it states that a matrix solves its own characteristic equation. what was the characteristic equation here if we write it in terms of like lambda? The characteristic equation was what? It was minus lambda cubed equals to 0, right? That's the characteristic equation. See, the matrix solves that. A cubed minus a cubed is in fact minus a cubed is equal to 0. So I knew this is what the Cayley-Hamilton theorem tells us, all right? So I knew a cubed was going to be 0 here before we did that matrix multiplication. I already knew that was going to happen because I know the Cayley-Hamilton theorem. All right? Okay, so yeah. Don't worry, I'm not going to prove that in here. I won't prove that in Math 221 either. That is something that we prove quite a ways into the semester with Math 321. That one's not an easy one to prove. It's a somewhat deep theorem, this Cayley-Hamilton theorem. Okay, so, all right. So I think hopefully you realize what I'm telling you. This particular example, fortunate things have happened, all right? So like what's the method to solve this kind of problem when it's not so fortunate, all right? And I guess I probably should erase this. Work over here, actually. You guys have any questions while I'm resetting stuff here? So I need to derive a few properties of the matrix exponential for you guys so that we can use them. Let's see here. All right, so so the matrix exponential is like the exponential, and yet in other ways it's not. So it's important for us to talk a little bit about how the non-commutativity of matrix multiplication kind of spoils. So naively, you guys know this, right? E to the A times e to the b is equal to e to the a plus b, right? If a and b are scalars, right? This is true for the ordinary exponential. It's still true if a and b are complex, right? That's one of the things we've talked a little bit about this semester. This is just the scalar exponential. But for matrices, it's not actually true. So if I have like e to the a times e to the b, that's going to be like I plus a plus 1/2 a squared plus dot 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 dot, right? And over here you have the identity matrix plus b plus 1/2 b squared plus dot 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 dot, right? And if you start multiplying this out, what you get, right? I times I gives you I times a gives you a. Well, AI, right? But AI is just I again. And then I get like IB. That's it up to linear order. What comes after linear order is quadratic, right? So like what are the quadratic terms to think about here? We've got like what plus, I'll start with the I times 1/2 b squared. We got that one, right? And then we've got a times b. And then what? Oh, the 1/2 a squared, right? And I think that's it for up to quadratic order, right? So if I rewrite that a little bit, this is I plus a plus b, right? And then I'm going to write it this way, 1/2, factor out the half, okay guys? And that's going to give me a squared plus AB, well, not plus AB, plus what? Plus 2AB, right? Plus B squared. On the other hand, we can calculate e to the a plus b. How's that go? Well, that's I plus a plus b, right? Plus 1/2 a plus b times a plus b plus dot dot dot, right? And if we multiply that out, what do we get?
Same thing.
Is it though? See, because we get a times a, which is a squared, plus ab plus ba plus b squared. So it looks like the same thing, but it's not. It's not. Why? Because a times b does not have to be equal. Yeah, it's not commutative. It does not have to be equal to b times a. All right? A times b does not have to be equal to b times a. These don't have to match, since ab is not equal to ba generally. These are not equal. On the other hand, if we did know that a times b was equal to b times a, in other words, if the matrices commuted, well, then we'd be fine. Then we could actually, carry out the mathematics and show that these two expressions are equal, right? So there's a theorem. There's a theorem to write down here, which I won't prove in general, but I mean, I've given you just the proof up to quadratic order here, and the theorem is simply this. If a times b is equal to b times a, then e to the a, e to the b is equal to e to the a plus b. All right?
Will that be specified in like if A and B are equal to B?
Well, we don't tend to find ourselves actually doing this calculation much for problems in here, but we needed to know it for a derivation I'm about to do. And there's another place we use it. Like, here's a place where it's obvious, right? How about a and minus a? A times minus a, does that commute? Well, that's minus a times a, right? Which is equal to minus a times a, right? So in that particular case, if we put b equals to minus a, they certainly commute. And that's important because I have e to the a times e to the minus a is equal to a plus minus a, which is also known as 0. What happens when you feed the 0 matrix to the matrix exponential? You get the identity matrix, and that shows, what does this prove then? So e to the a inverse, right, is equal to e to the minus a. I wrote it over there with a time multiplying the a. That doesn't change anything, all right? We need the time to be there for our application to differential equations, right? But if you don't mind, I'm stripping the time out of these algebra discussions because it makes it easier to see. So you might wonder, and I mean, no one's asking me, but I'm pretending you're asking me, well, okay, well, if they're not equal, when they don't commute, well, what happens, right? You might ask that question, what happens? And the answer, what happens, is the following. E to the a times e to the b is actually equal to e to the a plus b plus 1/2 the commutator of a and b, plus or minus, because I forget, 1/12. Like, it's not really plus or minus, it's like genuinely plus or minus. I just don't remember which is which. 1/12 b. That's not like, that's a plus minus concerning my memory. But these are nested commutators. Like here, AB is by definition AB minus BA. This particular construction appears all throughout quantum mechanics. Like in quantum mechanics, we look at the commutator of two operators. Operators act on physical states. The eigenvalues of the operator are the observables. All right. And it turns out if two operators have a commutator which is 0, it means they can be simultaneously observed. For instance, the position and the momentum operator, when you calculate their commutator, it ends up being non-zero, which corresponds to the fact that you can't precisely measure position and momentum at the same moment in an experiment. This is known as the Heisenberg uncertainty principle. But anyway, so this is the matrix algebra that you need to do in order to, like, this is how the law of exponents is modified in the presence of anti-commuting matrix, not anti, but non-commuting matrix multiplication. You have, and this goes on, it's like an infinite series of nested commutators. This is known as the Baker-Campbell-Hausdorff relation. And it's a fundamental formula for understanding like equations we write down in modern physics. Because modern physics, we look at fields which have matrices attached to the fields that represent physical symmetries, like SU2, SU3 type things. This has to do with like the strong force, the color force, these sorts of things, weak force, and other less exciting things. But in short, like matrix representation theory is part and parcel of understanding quantum mechanics in its like most recent formulation, the so-called standard model and all that. That's obviously not in this course. I just mentioned it because these are other things you can do with matrices if you want to study further. So fortunately, we don't need this. I won't require you to know it. I just mention it for breadth. All right. So, I mean, if you want me to just talk about things I test on in here, I could do that. But I really like to talk about this stuff, so then I'd have to test on it. You don't want that, right? So, okay. All right. I think the homework is pretty expansive in terms of like covering what is going to be tested on here, and then a little bit. Okay, anyway, so that is one of the things we can do with this formula, right? Like that. But there's more. There's more. See, because the other matrix which commutes with everything is the identity matrix, right? If I have the identity matrix times the matrix M, it's equal to M times the identity matrix, right? That's another thing we should notice. You know, the identity matrix, which is, you know, this thing. Zeros everywhere else, right? This thing commutes with everything. That's one thing we should notice. Another thing that it would be good for us to notice is that if we have e to a diagonal matrix, well, that's equal to, you know, like the identity matrix, right? Plus the diagonal matrix plus 1/2 the diagonal matrix squared plus dot dot dot. And when you calculate, if you square a diagonal matrix, all you do is you square the diagonals. So when you work this out, what you get is like 1 plus, you know, d1 plus 1/2 d1 squared plus dot 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 dot. And then you got like 1 plus d2, 1/2 d2 squared plus dot 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 dot. And this goes on. 1 plus dn plus 1/2 dn squared plus dot dot dot. I don't know if you can recognize what we're looking at here, but what you get when you exponentiate a diagonal matrix is you get a diagonal matrix where on the diagonal you have the Maclaurin expansion for the regular exponential function in each spot, right? This is e to the d1, e to the d2, and so forth. So like, sorry, kind of got squished, but so the matrix, the exponential of a diagonal matrix is the diagonal matrix of the exponentials forming the diagonal, which is super nice. All right, so now we have all of the necessary toys out in front of us. I can now derive for you what I like to call the magic formula. You might say, why is it the magic formula? The answer is simply that it's where the magic happens. So the magic formula can be written for any complex scalar lambda, or the real scalar lambda. But we'll learn that it's most interesting in the case that lambda is in fact an eigenvalue. Nevertheless, this identity can be written whether or not lambda is technically an eigenvalue. Like this is just an identity, a formula which holds for an arbitrary matrix and an arbitrary scalar as a consequence of the algebra of the matrix exponential that we're looking at here. So let me write it down for you guys. Yeah. So here it is. So I'm going to derive it for you guys. We'll start out with e to the ta. All right. There you go. And then I will rewrite that as e to the t times a minus lambda I plus t lambda I. So far all I've done is added 0. All right. Notice here that this matrix is basically it has the form a constant times the identity, right? So this commutes with the other matrix there, right? Because a constant multiple of the identity will commute with any other matrix. So in this case, the law of exponents works, and I'll just rewrite this as e to the t lambda I times e to the t times a minus lambda I, using the fact that those are commuting matrices, so the laws of exponent apply in this particular case. But what is e to the t lambda I? What kind of matrix is that? E to the t lambda I is e to the what? Like t lambda, t lambda, t lambda, t lambda, like that, right? And by the identity I was just sharing with you guys, that is actually the matrix e to the t lambda, e to the t lambda, e to the t lambda, right? By this calculation over here. But we've got the same scalar everywhere, right? So we can just pull that out. This is really just e to the t times lambda times the identity matrix, if you look at it, right? So I will use that to simplify this as simply e to the t times lambda, that's a scalar, times the matrix I. Okay? I'll put some color in here to make sure I'm not losing you guys. So that's this piece is right here, all right? And then, how about the other piece? What do we got? This here, that expands as what? The identity matrix, right? Plus t times a minus lambda I plus t squared over 2, a minus lambda I squared, plus t cubed over 3 factorial, a minus lambda I cubed, so forth and so on forever and ever. All right. Let me record this formula over here for our future use. We have that e to the ta is equal to e to the lambda t times the identity matrix plus t times a minus lambda I plus t squared over 2 a minus lambda I squared plus t cubed over 3 factorial a minus lambda I cubed, and it goes on. This is the magic formula right here. All right? So let's see what happens. First of all, first order of business. If a minus lambda I times u is equal to 0, right? That would mean u is a what? We had a name for these, yeah? What are these called? What's that make u? Eigenvector, right. So u is an eigenvector. You'd be like, well, you didn't say it's non-zero. Fair enough. You being non-zero, okay? An eigenvector with eigenvalue lambda, right? What happens when we take, the matrix exponential and we hit it, multiply it on the right by an eigenvector? Can we do that? Does that make sense? We're talking about a matrix times a column vector, right? That is a meaningful multiplication. N by n by n by 1. So this is an n by n matrix. This is an n by 1 column vector. So the answer is, again, a column vector, all right? Which one is it? What happens when we hit? So look what happens. So we have e to the t lambda times the identity matrix plus t times a minus lambda I think that's enough, plus dot, 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 right? Multiply that series by u. What happens when the u gets there? What happens? We're left with what? Yeah, e to the t lambda times iu, very good. A minus lambda I times u, right? Yep. The next thing, if I was to write it down, t squared over 2, a minus lambda I times a minus lambda I. I won't usually write this out, but just to be clear, like that's the next thing, a minus lambda I squared. But what happens, what's the deal? A minus lambda I times u is equal to what? 0. So this is 0. This is 0. 0 times 0, 0, 0, 0, 0, all 0. And you're just left with what? Yeah. So we could drop the identity, right? So this is just what? This is just e to the t lambda times u. This is our eigensolution. We already knew about this. We've been finding these already. We've been using these to construct our solutions, right? But if you take the matrix exponential and you multiply it on, on its right by an eigenvector, out pops the eigensolution, right? So we already knew about this one. And so next up, we need to make a definition because there's more. So here's the definition. If we have a minus lambda I times, let's say, u sub j is equal to u sub j minus 1 for j equals to, let us say, 2, 3, all the way up to k. And we also know that a minus lambda I u1 is equal to 0, then this set here, u1, u2, dot, 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 uk is a k-chain of generalized eigenvectors with eigenvalue lambda. So I need a little bit more language here. If a minus lambda I times to the p power times w is equal to, let us say, 0, and yet a minus lambda I to the p minus 1 power times w is not equal to 0, then w is generalized eigenvector of order p. For example, what is a generalized eigenvector of order 1? Let's see, 1 minus 1 is what? 0? Any matrix to the 0 power is the identity matrix, okay, by definition. So this collapses down to the statement that a minus lambda I times w equals to 0, and w is not equal to 0. That makes w a what? That makes w an eigenvector, you see. So for p equals to 1, we're just back to eigenvector. But for p equals to 2, it's something new, all right? And the theorem here that we can state, and we should probably work this out, is that given k chain as just given, as described over there, right? We can prove that a minus lambda, well, this is given, right? A minus lambda I u1 is equal to 0. A minus lambda I times u2 equals to 0. Not equal to 0, it equals to what? It's equal to u1. That's given, right? What does that imply? Multiply that equation I just wrote by a minus lambda I, what happens? What happens when we multiply that equation I just wrote by a minus lambda I? We get a minus lambda I squared, u2 equal to what? What was a minus lambda I u1 equal to, though? By assumption, that was 0. So therefore, u2 is generalized eigenvector of order 2. It's a generalized eigenvector of order 2 because a minus lambda I squared acting on u2 is 0, yet a minus lambda I acting on u2 is equal to u1, which is not equal to 0. What do you guys think happens with u3? That's given to be equal to u2, right? What happens if we take that equation and multiply it by a minus lambda I? What's it give us? So that's that a minus lambda I squared acting on u3. Well, that gives me, it gives me this, right? But what's this? This is equal to u1, right? So a minus lambda I squared on u3 gives me back u1. What happens if I multiply by a minus lambda I another time? I get a minus lambda I cubed acting on u3 is a minus lambda I acting on u1. This was given to be 0, yeah. So therefore, u3 is generalized eigenvector order 3. This trend will continue, right? Like, what's uk going to be? uk is going to be a generalized eigenvector of order k. Okay? Sorry. That was horrible. I regret nothing. I regret there being a window in this room, actually. That's what I regret. But any questions here before I go on? Almost forgot. There's the handy dandy, exciting sentence sheet. There you go. So like if we work this out, we would have, next up we'd have like a minus lambda I u4 equals to u3, a minus lambda I squared on u4 is u2, a minus lambda I cubed on u4 is equal to u1, and finally a minus lambda I to the fourth power on u4 is equal to 0. So what happens then when we multiply the magic formula by a generalized eigenvector? Yeah? What happens then? So let's look at that. If we take e to the ta times u2, that's e to the lambda t times I u2 plus t times a minus lambda I u2 plus what? Plus stuff that goes to 0. Plus stuff that goes to 0, because a minus lambda I squared acting on u2 is 0. So the series truncates just to these first two terms, and we get e to the lambda t times u2 plus tu1. That's what happens there. And if we do e to the ta times u3, we get e to the lambda t times I u3 plus t times a minus lambda I u3, 1/2 t squared a minus lambda I squared u3, plus stuff that goes to 0, right? And so what that gives me is e to the lambda t times u3 plus t times u2 plus 1/2 t squared times u1. And so this is how we get multiplication by t or t squared in our solutions for systems. They're coming from generalized eigenvectors, right, of order, order 2 gives you a t, order 3 gives you a t squared, right? So, any questions? So the method then to solve a system of differential equations is to find all the eigenvalues, find all the eigenvectors you can, and then wherever you're missing eigenvectors, you need to go looking for generalized eigenvectors, and then you use the generalized eigenvectors multiplied by the magic formula that produces the other solutions. That's the technique that gives you a general solution to any of these problems. Now there's a wrinkle. It could be that the eigenvalues are complex. In that case, you have to find complex eigenvector and then complex generalized eigenvector. Every complex generalized eigenvector gives you a pair of real solutions by looking at the real and imaginary part, just like we did with the eigensolution already. All right? And that's where you can get formulas like t cosine and t sine in your solutions. All right. Let me actually work a problem for you guys. Now that we have the machine, let us use it. Uh-oh. So I'll start out with a relatively easy example for us. I don't know if I have a uglier one offhand. I guess this is example 3. Suppose you wanted to solve dr dt equals to a times r with a equals 2. We'll do 3, 1, 0, 0, 3, 1, 0, 0, 3. right? Let's see if we can solve this thing. What are the eigenvalues?
3.
I heard a 3. Good answer. How many times? Still a good answer, right? Yeah, 3. 3, eigenvalue 3, 3 times. Everything's 3. Yeah, so since it's triangular, the eigenvalues appear on the diagonal. Of course, we could calculate it. The determinant of a minus lambda I here is the determinant of like 3 minus lambda, 3 minus lambda, 3 minus lambda. You got your 1 here, your 0 here, 1 here. And so we get 3 minus lambda cubed, right? So yes, my eigenvalue is 3, and the algebraic multiplicity is 3. How many eigenvectors do we have? Well, let's find out. So let's look at a minus 3i, right, times u1, which is what? Oh man, this is the same problem, isn't it? Look at that. Deja vu all over again, right? So apparently v equals to 0, w equals to 0, and u is free. So I can let u1 equal to what? Yeah, u1, I heard a 1, 0, 0. I like that. Right? And we know that that's going to give me the solution. E to the ta times u1 is simply equal to e to the 3t times u1, right? This is going to be my eigensolution. I don't need to explain to you guys where that came from, because we worked it out in general. So what's next? Well, we'd be stuck before break, right? That's all we could do. We'd just be like, well, I don't know. There's 2 other solutions to find here. What are they? But now we can go looking for a generalized eigenvector of order 2. So what you do, the equations I wrote down there for the k-chain, those are the chain conditions. You can work the chain backwards for a lot of examples. And so what I can look for is I can say, okay, so I want u2, right, not equal to 0, such that what? Such that a minus lambda I times u2 is equal to u1 for lambda equals to 3, right? So specifically, I need to solve. We already worked out that matrix, right? So that's this 0, 1, 0, 0, 0, 1, 0, 0, 0 times the u2 vector I don't know yet, u, a v, a w. And now we don't have 0 over here now. Now we've got the eigenvector, which is 1, 0, 0. Yeah? So what equations am I up against this time? Well, I've got the first one gives me v equals to what? 1. Well, we can't make v equal to 0. V has to be 1. Second equation, I get what? I get w equal to 0. And then u is free. However, unlike our previous times, we do have the option to make u equal to 0. Why? Why can I make u equal to 0 here? Why is that a permissible choice? It's still a non-zero solution, right? So that's the difference. We can make u equal to 0, and that would make our answer most nice. So we'll do that. That gives us u2 equal to 0, 1, 0. All right? Then e to the ta times u2